So far, we've looked at two different examples where we've calculated both the mean and the median. The first example we looked at was on NFL salaries, and the second one was on speed. Let's take a look again at our salary example. Remember, we said that in our salary example, if we looked simply at the histogram for the Tampa Bay football roster in 2021, we can clearly say or be able to describe this distribution as being skewed right. We see that we have an awful lot of data by the height of this bar here. An awful lot of data is occurring in the first bar of our histogram, and then we are moving out with less and less data out here towards the tail. Now, my mean and median for this data set we saw was given here. Remember, we had a mean or an average salary for this roster at 2.6 million versus the median, which was here at 0.9, so less than 1 million. And when we are considering these types of distributions, when we have skewed data, we understand that that average salary is not going to be the best use of or the best way to be able to describe our data. Instead, when we have skewed data, we actually want to look at the median because it's going to give me that 50% mark. We know 50% of the players earn less than 900,000 and 50% earn more than 900,000. Contrast that with the second example we did on the speed, and just looking at the shape of the histogram, again, we had a normal distribution or a bell-shaped distribution, which we said was a symmetric distribution. When we calculated both the mean, median, and mode, or all three of the mean, median, and modes for that particular data set, we recognized that both the mean and the median were really close to each other, and that is indicative then of a symmetric type distribution. So this leads us to a conclusion then about our shapes and of our histograms and how they're related to both the mean and the median. So here we see when we want to talk about skewed data with the leftmost graph here or image and then our right graph over here. Skewed data is going to have our mean moving to either side of our median. Now, our median is not going to change. Remember, the median is just the middle number of a data set. It's your average that is moving either smaller or larger depending upon the data, but the median stays the same and your mean is moving either left or right of that. When we have skewed left data, notice that the mean is less than the median. As I've stated before, the mean is going to pull towards the tail, so that means the mean will be smaller and therefore less than the median here. When we have symmetric data, like you see here in the center graph, we end up with a mean that is equal to the median. So that's just a characteristic of both the normal, uniform, as well as a binomial distribution. Symmetric data is going to have your mean and median equal to each other. And then finally, what we have over here, again, our mean, we have a skewed right distribution, and our mean is actually to the right of our median. So again, it's pulling towards that tail. All of that is to say that if the median stays still, but the mean is able to move around and move left or right of that median, depending on any values that you might have that are really, really big or values you have that are really, really small, we would say that the mean is not resistant to outliers, or the mean is not resistant to very large or small values. Another way to state that you might see is that the mean is easily influenced by these very large or very small numbers. Because again, the mean is the sum of all the numbers in the data set. And when we have very large or very small numbers in that data set, it's going to either inflate or make the numbers very small that we are then dividing. As opposed to the median, which is simply the middle number of a data set, which is not going to move no matter whether you have very large numbers overall or very small numbers. The halfway point of a data set is always just going to be the halfway point of a data set.